Alright, boys and girls, welcome to our first video lesson in Chapter 3, Section 1, our lesson on exponential functions. Alrighty, here we go. Okay, these are just some rules of exponents which you should remember from Algebra 1 and certainly from Algebra 2, such as when you multiply two exponents with the same base, you just add the exponents and you know why about that. When we're dividing exponents with the same base, we subtract the exponents. If I'm raising an exponent to a power, I multiply the exponents. Certainly if you raise a product, if you multiply two things and raise that product to the power, you're raising each of the factors to the power. Same thing with a fraction. If you raise a fraction to a power, you're raising both the numerator and the denominator to the power. You know these basic rules. Any number to the 0 power is 1. The exception to that, of course, is 0. Okay. You also know that any number to the first power is itself a number raised to a negative a base raised to the negative 1 is the reciprocal, right? So a to the negative 1 is the reciprocal of a, and a base raised to a negative exponent is the reciprocal of the positive exponent. And of course, if you raise a fraction to a negative exponent, it is the power of the fraction the reciprocal of it. Okay. We also know that 1 to any power is always 1, and our exponential property of equality says if a to the x is equal to a to the y, then x is equal to y. These are all things that you should know, that you know from Algebra 1 and a little bit in Algebra 2. All right, moving along. I want you to just put these down into your notes. These are some of your powers. Okay, the powers of 2 are written here in red. In other words, 2 to the 0 power is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. I would expect you to just be familiar, at least, all the way with the powers of 2 up to 2 to the 10th, which is 1024. Okay? The powers of 3, 3 to the 0, of course, is 1. 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. I would expect you to be at least familiar with all the powers of 3 up to 3 to the 6th, which is 729. The powers of 4 are here in purple. 4 to the 0 is 1, 4 to the 1 is 4, 4 to the second is 16, 4 to the third is 64, 4 to the fourth is 256, and 4 to the fifth is 1024. And lastly, in green here are powers of 5. 5 to the 0 is 1, 5 to the first is itself 5, 5 squared, 5 to the third, 5 to the fourth, and 5 to the fifth. Do I want you to memorize these? Well, I would love it if you did, but at least be familiar with them, so when you see them, you recognize a number like 625 as a power of 5, as opposed to just a normal number like 325, which is not a power of 5. Okay, I do want you to know your squares up to the square of 20. Okay, they are written in blue. So 1 squared is 1, 2 squared is 4, 3 squared, 4 squared, 5 squared, 10 squared is 100, 11 squared is 121, 14 squared is 196. Okay, all the way up to 20 squared is 400. Stop the tape if you need to write these down. I want you to know your cubes to 10. Your cubes to 10. So 1 cubed is 1, 2 cubed is 8. 7 cubed is 343, and 10 cubed, of course, is 1,000. Again, stop the tape, write these down from this slide and the last to make sure you have them into your notes. Okay, I have a poem. Of course, you know this poem. When in doubt, make an XY chart. So let's look at the exponential function, y equals 2 to the x. This is an exponential function because the exponent for your first time, not counting last year, of course, is our exponent is now in our variable is now in the exponent of our function. Notice that we have y equals 2 to the x power as opposed to a polynomial function where we have y equals x to some power. Our variable is now in the exponent. Hence, it's an exponential function. So if I look right here, we have when x is 0, so when x is 0 right here, here's my x. If I throw in 0, I'm going to have y equals 2 to the 0, so y would be 1. If x is 1, we have y equals 2 to the first power, which is 2. If x is 2, we have y equals 2 to the second power, which is 4. If if x is 3, y would be 2 to the third power, which is 8. If I take the reciprocals of those now, if x is -1, it's 2 to the -1 power, which is the reciprocal of 2 to the first power, which is 1/2, or if you prefer, 0.5. 2 to the -2 would be 1/4, which is 0.25. And 2 to the -3 is 1/8, which is 0.125. Okay, if I think about y equals 10 to the x, 10 to the 0 is still 1, 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. Notice our function gets big very, very quickly. 10 to the -1 is 1/10, which is 0.1. 10 to the -2 is 1/100th, which is 0.01. And 10 to the -3 is 1 over 1,000, which is 1/1000th, which is 0.001. Okay, if I take those ordered pairs I just figured out in the chart from our last slide, and I put those here in my graph on blue, we'll do the 2 to the x power. So we had a point at 0, 1. We had at 1, 2. We had one at 2, 4. We had one at 3, 8. Okay, if I kept going to 4, that would be up here at 16, and you can see now that this gets big very quick. On my other side, I have one at -1, 1/2, -2, 1/4, -3, 1/8, etc. Our graph is going to look something like this. I'm doing my best to draw this with my marshmallow. Okay, there is what your exponential graph looks like. It shoots to the right very, very, very quickly, so it shoots up on the right very, very quick, and on the left it hugs the x-axis, so it's asymptotic. Our x-axis is an asymptote on the left. Okay, a couple things just to think about. If b was equal to 0, our base, we would not have an exponential function. Basically, our graph would always be 0, so that doesn't work. If b is 1, basically that would be 1 to any power is always 1, so that would be a horizontal line, so that's not an exponential function. That would be a horizontal line at 1. b can never be negative. B cannot be negative, because if we had that, then we would not have a function at all. It would pop back and forth. It would just be all messed up. Some of the answers would be imaginary. Okay? If b is a fraction, what happens now, I'll write this in blue, is our graph gets flipped around. It's very similar, but it's asymptotic on the right, and it shoots up going to the left. Okay, so this would flip it if b were a fraction. Now, what is the domain of this function? Notice that x can be anything, so it's all reals. And what is the range? Well, notice that it's always positive. Our y's are always positive. In fact, it never even gets to 0 because the x-axis was an asymptote. So y is greater than 0. Okay, so let's just talk about exponential functions with the a, the h, the b, and the k. Okay, and again, it's the same transformations that take place with all of our other graphs. Okay, the a is our vertical stretch. If a is a number, our graph gets stretched out vertically. If a is a fraction, it gets squished. It is a compression. If a is negative, of course, then it's going to reflect over the x-axis and turn upside down. The b part of our graph represents the rate of growth. If b is a fraction, we just went through that. It is reflected over the y-axis. B, we just went through too. B cannot be 0. B cannot be 1. And b cannot equal a neg. Okay? The bigger b is, the bigger our graph is going to shoot up even faster as we move to the right. The h, of course, is our horizontal shift, and the k is our vertical shift. When we talk about an exponential function, we talk about the critical point is the y-intercept. It's typically at 0, 1, because our graph is going to look like this. There's our one critical point. Okay, the critical point, if you're a mesmerizer, which I am not, but your critical point is going to be at the ordered pair h, k plus a. Okay, and know that the asymptote will always be the k value. So, why don't you guys take a quick minute, look at these 1, 2, 3, 4, 5 functions. I'm hoping you can see what they are, the a, the b, the c, the d, and the e. I want you to figure out which one is which, match them up. Note, the functions are not necessarily drawn to scale. Go ahead and give it a go. Okay, if you look at the first two, y equals 2 to the x and y equals 10 to the x, those are going to be very similar functions, but y equals 10 to the x is going to shoot up much faster than y equals 2 to the x. So we're looking at our graphs. B and D are our basic exponential functions. B must be the second one because it shoots up faster, and D would be our first one because it does not shoot up. It shoots up fast, but not quite as fast. Okay, 3 would be the exact same thing as number 1, but the whole thing was raised 2 units up, so that is equation C. Notice that in number 4 now, we have a negative exponent, and the whole thing is moved down 3, so that's going to be function A. And the last one, we have an A of negative 1, so our graph gets flipped over. It's also raised 3, so that would be E. It's an upside down exponential curve. Okay? All right, let's practice graphing right now. Looking at this one, our A is going to be 1. This is like written as 1. Okay, it's 1 times 5 to the x. Our B, of course, is 5, so it shoots up pretty quick. Our H, there is no H, so it's 0, and there is no K, so it's 0. So let's go ahead and graph this guy. My critical point, my y-intercept, is at 0, 1. It's just our regular exponential function, so it's going to shoot upwards when we move to the right, but please note that this graph will always continue to go to the right. It just gets big, very, very big, but our domain is all real numbers. And down on the left side, it's going to approach that x-axis. It's asymptotic on the left. It's approaching that x-axis, but never quite getting there. So therefore, from 0 on down, our function does not exist ever in the negative area. Our range is all positives. Our domain is all real numbers. Looking at this right now, we can see that our A is again 1. Tricked you. You thought it was 3 halves. No. Our B is 3 halves. Our H in this case is neg 2. Be careful that plus 2 is in the exponent. Don't forget that H's always look reverse of what they are. And K is 0. So let's just talk about what happens if there were no H. Our critical point would again be 0, 1. And I'll do this in red, and then we'll move it. It would be asymptotic on the left. It's going to shoot up, not quite as fast on the right. But then now what happens, because our H is negative 2, this whole thing is going to move 2 places to the left. So basically our ordered pair, our critical point got moved. It's still going to shoot up to the left, to the right, and it's asymptotic on the left. The whole graph just moved. You guys try graphing this one. Stop the tape and go ahead. Okay, you should have found that the A was negative 2. Our B is 5. Our H is 0, and our K is negative 3. Also note we have a negative exponent, so just be careful there. Let's just talk about what if this were 2 times 5 to the x. If it were y equals 2 times 5 to the x, that means it's an exponential function that gets stretched out. So our critical point would be 2. It would shoot up very quickly because now it's stretched out. It's going to hug that x-axis. On the left-hand side, it's asymptotic on the left side. But now the fact that it's negative means it's turned upside down. So, just taking the negative 2 part means it's going to look like this instead, upside down. But also now the fact that we have a negative x, which means it's also flipped over the x-axis. So it would actually look like this. I'm sorry, flipped over the y-axis is what I meant to say. It's flipped over the x-axis because of the -2. And then lastly, the whole thing moves down 3. So I'll do that in, we'll get a new color here. We'll do it in green. Okay, so this whole thing just moves down 3. So our graph is actually going to look something like this, where the asymptote is here at y equals -3. Okay, a couple of equations you need to remember, I hope. But the compound interest formula right here, A equals P times 1 plus R over N, all raised to the NT. The P represents our principal. The annual rate is written as a decimal, that's our R. Our time is in years if it's an annual rate. Could be a different time, but it's going to have to be the rate. Okay, and the amount of money at the end is the A, and the N is the number of payments per year. This is our compound growth formula. Okay, so here's our exponential growth, same idea, same exact formula, and this could be any type of growth. We have another formula you need to remember. P equals 1/2 T to the T over H. This is the half-life formula. There's also one more that you need to remember, and we will derive this in class, I promise. It's actually pretty groovy. It's the continuous growth formula. A equals P times the number E, which is an irrational number, all raised to the RT, and you probably remember APERT from last year. So a couple quick problems. We'll do these in class, but I want you guys to use our compound interest formula right now. We know how much money would you have after 49 years compounded annually. So we know now that our A is what we're looking for. Our P is 1,000. Our R is 0.08. Notice I'm writing that as a decimal. Our T is 49, and if I'm compounding it annually, my N is 1. So my equation is going to be A is equal to 1,000 times, in parentheses, 1 plus 0.08 divided by 1, right, raised to the NT, which is 1 times 49. I'll let you guys pull out the calcs, do that math. Okay, you should have had $43,427.42. Not bad for $1,000. Okay, if we do this compounded quarterly, okay, our A is again what we're looking for. Our P is 1,000. Our R is 0.08. Our T is 49. But this time, because I'm compounding it quarterly, our N is 4. Everything's going to be the exact same thing now, but this time our N is 4. So A is equal to 1,000 times 1 plus 0.08 divided by 4, which of course is 0.02, raised to the 4 times 49, which of course is 196. Okay, so whip that into your calc. See what you get. Very good. You get $48,487.93. Why don't you guys do the last two? Everything stays the same in 3, except our N is now going to be 12. In the fourth one, everything stays the same, but this time our N is 365. And the last one, you have to use the APERT formula and see what you get. Okay, for compounded monthly, you should have had $49,749.03. I'm sorry, 4 cents if I round correctly. Okay, for compounded daily, you should have had $50,378.80. And for compounded continuously, you should have had $50,400.44. All right. Okay, why don't you guys do this last one on your own? It's just like what we just did, but this time our R is 2%, so our R equals 0.02. Our time is 10 as opposed to 49, and our P as opposed to 1,000 is going to be 2,500. But everything else stays the same. Notice that our N is going to go from 1 all the way up to continuous. I want you guys to find each of those 5, let's see, 1, 2, 3, 4, 5, 6 answers. Okay, and the first 6 people to email me the answer for this following question, I'll give you a bonus point on your next test or quiz. What is the difference between the continuous growth and the compounded yearly growth? This one and this one, what is their difference? First 6 people to email me the answer, I'll give you a bonus point. And lastly, I promise you in class we will go over this problem and I will show you a shortcut how to use to solve this problem with a function on your calculator, so you would only have to do it once. All right, folks, have a great day. We'll see you soon.